Welcome back to the CANA Connection Podcast. On today's podcast, our guest host is, again, Kassie McRostie, and she's going to be talking with our other fellow CANA, Mr. Connor McLemore, about all things good with the CANA Core Algorithm. So, Kassie, without further ado, take it away.
Yes. Hello, my name is Kassie McRostie. I'm the digital media coordinator here at CANA, and today I am joined by Connor McLemore. That's how you say it, right?
Close, McLemore. Yeah.
McLemore. Sorry. Introduce yourself, your role at CANA.
Yeah. So I'm Connor McLemore. I've been with CANA for a little over 4 years since I retired from the Navy. I'm a principal operations research analyst. The last couple of years in the Navy, I was in operations research jobs, so it was a fairly seamless transition to come to CANA, which is a very operations research focused company. In the Navy, 20 years Navy, E2C Hawkeye Naval Flight Officer was my background. But my last couple tours in the Navy, I did a teaching tour at Naval Postgraduate School in the Operations Research Department. I was also the program officer. And then from there, I went to the program sponsor, which is in the Pentagon, OPNAV N81, which is the analysis division on the Chief of Naval Operations staff. And I retired out of the Pentagon. I live in Reno, Nevada, with my wife and 3 children, and very much enjoying working for CANA. Lots of interesting operations research problems.
Yeah. So today we're going to kind of talk about the CANA Core algorithms. This is, I guess, more newer to CANA. If you could kind of tell us a little bit about what CANA Core Algorithms is and what your involvement in it is as well.
Yeah. So CANA Core Algorithms are the projects that CANA has done that CANA thinks have applicability to broader sets of organizations that are general enough to be used by potentially lots of different organizations, and not just military organizations, but other organizations as well. So I've had close involvement in certainly 2 of the CANA Core algorithms. So I did work for about a year on our distribution network model, which is a multi-commodity network flow model, which uses an ant colony algorithm. If I get too technical on the OR stuff, Kassie, cut me off, and I'll be happy to speak to whatever audience is appropriate. But I think CANA probably has an OR audience. And anyway, that was just that was a very general algorithm in the sense that if you wanted to move stuff from one location to another location through a network using connectors, it was widely applicable, right? So we have CANA has a Marine Corps client who's certainly intimately interested in that and using it on a regular basis, but it has a wide applicability beyond the Marine Corps client. And so that would be a good example of a CANA Core algorithm. The thing I think we're here to talk about today is our Entourage model. So Entourage is the latest CANA Core algorithm, just got approved as a CANA Core algorithm. This was work that we did for Department of Navy Energy. And so we did some analysis for Department of Navy Energy, and then that resulted in algorithms that are CANA's that we think have broader applicability. So what Entourage is if you have a high value unit to protect, it can be moving, it can be stationary, whatever, and you want to throw up a defensive barrier of manned and or unmanned systems to attrite incoming attacks, that's what Entourage does, right? So you say what you want your barrier to be, where you want it relative to the high value unit, what the attacker is, and then it's going to give you what's called the what we're using for an objective right now is probability of rate annihilation, but you can imagine lots of other objectives as well. So what's like the motivating force for doing this modeling, right? Well, this was a Navy client that we did the analysis for, and you can imagine just reading the open source news that drone and missile attacks are becoming a lot more prevalent in today's warfare. So you can think of Ukraine, you can think of attacks Iran is launching, and you can especially think of Houthi rebels attacking merchant ships in the Red Sea, right? And so, what the Navy has is these absolutely exquisite ships with these absolutely exquisite weapons, right? And the problem with that is that it's not just the cost. Like DoD's budget's pretty big, right? If it was just a cost issue, you could probably eat it. But these weapons are essentially irreplaceable, right? So once the Navy fires one of these exquisite weapons, which can cost tens of millions or hundreds of millions of dollars, lots of money, that weapon's gone. That magazine has to go back to some port to be reloaded currently, right? And so it's not just and forget the reloading. It's also the rate at which you can acquire these weapons, right? So the assembly lines to build these weapons take a really long time. It's not like there's just all these weapons that you can just throw on an airplane or a ship or something and bring them back out and you're good to go. So using exquisite weapons against really, really cheap, attritable drones and missiles is not a sustainable strategy financially and due to the replenishment time and cost, right? And once you use those silver bullets, they're gone. That was a pretty long explanation, but now I'll get to the point of what Entourage is doing. So what Department of Navy Energy was interested in specifically was could you throw out a barrier of defensive systems? So any domain, right? You can imagine an unmanned boat floating on the ocean. You can imagine an aircraft. You can even imagine something subsurface, right? Let's say there's a unmanned torpedo coming in or something. Maybe it's possible to intercept that. And what they wanted to know was, what should the Navy be purchasing in terms of these portfolios of systems? And that's a pretty interesting problem, right? And it's kind of hard. So given that you have a whole bunch of potential systems, can you detect attackers by throwing a bunch of them out there along this barrier? Can you intercept attackers? And then a lot of people have done that work, right? That's pretty mature work that we could shamelessly take from other published academics and that sort of thing. But what we did that I think is a little unique is along with detection and intercept, we added communications and we added the energy aspect. So, given that, let's start with communications, right? So if you push a barrier out 100 nautical miles and you only have 50 nautical miles of communications range, that doesn't mean you're out of luck, right? Potentially you can put a relay drone out there and it can, 50 nautical miles out and it can bridge the 50 nautical mile gap, right? So that's the sort of thing we have to do in terms of the laydowns of drone stations that we're putting out there. We have to take into account communication relays. And what we're really checking is we're using an adjacency matrix approach to make sure we have a fully connected mesh network out there. So everybody can talk to everybody else, right? And the idea there is there's no way that you're going to get approval to intercept an attacker if you're not talking to someone who has authority to give that approval. So we're not hopeful. I don't want to say it would be challenging to just throw out a barrier of drones that's operating autonomously, right? We don't think that's currently realistic. So what we're doing is we're saying you're going to have your buried drones, but they're going to have to call back and say, hey, look what I'm seeing. I'd like it's a drone or a missile or a torpedo. Can I intercept it? And then once it gets the approval, then it's off and running, right? So that's communication. So we check the connectivity of the mesh network, and then we're using a greedy heuristic. And the reason I don't want to get too far into the algorithmic approaches, but there were really two goals here: was to use mature algorithms and to keep this thing blazing fast, keep it super, super fast, because you could use other algorithmic approaches, which might get you closer to mathematical optimality, but are far slower. And the speed and a good enough solution was much more important for us. The greedy energy heuristic was actually much harder to build than I thought it would be. But essentially, what I'm talking about with a greedy heuristic is these unmanned systems refuel greedily. So whoever's sort of next in line, you'll send out individual unmanned systems to their stations, and then if they don't have enough, there's a check on the front end to see, can it cover the entire time window that it's required to be on station? And if the answer is no, then that unmanned system is going to have to be backfilled at some point, right? And so that's where a lot of the checks come in. So we do things like, hey, if I'm on station and I'm out of fuel, is there another station out there somewhere that can pass fuel to me, for example? That would be like the first check, right? And then there's what we're doing on the front end as part of pre-processing is we're figuring out things like what's the order of what's the best order for refueling. So it's not willy-nilly. It's not like first in line. It's kind of like, hey, we think this station over here is going to be a good station to refuel from because it's close, things like that, right? So I'm going to say, okay, can I go to that station? Oh, I can get gas. I can get back. But meanwhile, within that gap, I still have to backfill with another unmanned system. And the other thing I should mention is that this whole problem aligns closely to my operational background, and that made it really nice to do this work because normally when you're building these sorts of algorithms, you got to seek out experts in whatever field you're building the algorithm for. Well, in this case, I had a lot of expertise in that I've done things like run combat air patrol stations and multiple combat air patrol stations and aerial refueling and that sort of thing. And so what was sort of interesting about this particular problem was that I thought it was going to be just like manned aviation, essentially. So we were going to establish this, what we're calling an unmanned engagement zone, where you're going to have interceptors on the leading edge, sensors on the leading edge. You're going to have interceptors on the trailing edge. And then, as threats enter this unmanned engagement zone, you're going to detect them and you're going to go through the whole process. And we're using a simulation approach to see if we can, how many intercepts we can consummate and what our probability of rate annihilation is. And then what we're doing is, over the simulation approach, we've wrapped an optimization to determine what the best overall stationing is, right? And so I thought it was going to be kind of boring. I thought it was just going to be like manned aviation, and it turns out it's not like that at all. And a big reason for that is I won't give away everything here, I guess, but environmentals and motion of the HVU, because the speed of these unmanned systems can be so much less than manned aircraft, right? So the environmentals and the movement of the ship matter a lot less to manned aircraft, which tend to be much faster. This sort of model allows you to say, hey, we can't, if this is the setup, if the ship or whatever the high value unit is moving in this particular direction and the wind is such and the attacker is of a certain speed, we can't consummate that intercept at all, right? We can't do anything about that. And so, where those bounds are for these portfolios of systems is kind of fascinating. So that was a long answer to your question, I think. But I guess what's the next one?
It's a long, thorough, but good answer to that question.
Good.
So no, go ahead.
No, go ahead, Kassie. I was just going to.
No, I was going to say, so basically, I guess one of my other questions, and you kind of answered it, is like what sets CANA apart and what sets this Entourage apart from any other company or, that does algorithms. And I'm probably not saying this in the right operational research language, but I guess what you said is communication and the speed of things. And when you were in the Navy, did you see these problems happening? And I guess that you're using your algorithm to fix now?
Yeah, I mean, so that sort of gets back to what I was saying about I didn't expect there to be a difference between how manned aviation operates and how these systems of unmanned systems would potentially operate, right? Mm-hmm. And the big difference is not just the environmentals, but it's also the number of unmanned systems that you might have to throw out there, and then the complexity in refueling. So again, manned aviation is pretty simple. Typically you have a refueling station somewhere out there, and you have your cap station that's pushed out there, but it's not that critically important where these things are positioned, right? Because you have communications typically isn't a huge issue. You have really long radio ranges and even satellite communications ranges and data links and that sort of thing. And you may not have that with drones, right? So for example, you're not going to have transponders on all your drones, right? And transponders are the things that tells other units what the drone is, right? So it's like that there's various types of transponders, but all you're going to have out there are radar contacts, right? Relative to manned aviation, where you have these really, again, advanced, exquisite systems where I can look and I can say, oh, that's a certain type of aircraft that's friendly, blah, 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 right? Whereas in contrast, forget operating off a destroyer. Let's, in theory, say that this system could operate off of a merchant ship, right, to defend a merchant ship transiting the Red Sea. Well, in that case, you're not gonna know what all these things are out there. What's realistic, perhaps, is that you detect an incoming attack by whatever means, and it could be a drone, it could be other sensors. Pretty agnostic as to all of that stuff. But once you have that, you have to classify it before you can kill it, right? Because what if it's just a family tooling around in a Cessna out there, right? That could be a disaster if you were to try to defend yourself and you didn't know what you were defending yourself against, right? So that's where you asked what's different or what's I think novel about what CANA's doing, and I think it's the combination of detection and intercept with communications and the energy considerations for these far more, I would say, complex combinations of systems. And the other thing I'll say that's novel about what we're doing is this tool is potentially useful as an operational planner, and that's what CANA's building it out towards. And what I mean by that is, if I had to establish one of these defensive barriers of drones, and I had a bunch of known drones, and I just wanted to know how to best employ them and where to station them and stuff, I could put all that into Entourage, hit run, and it would say, okay, put it at this lat long. Here's when you're backfilling, all that stuff, right? But where I think it gets interesting too, in terms of what CANA has, is we're also able to look at potential portfolios that you may want to purchase, right? But are uncertain. And what I mean by that is what's the right number of drones to put on what's the right number of drones of a type to put on a destroyer in combination with other drone types that have certain capabilities, certain refueling capabilities, certain comms capabilities, because the limitation might be comms, or it might be fuel, or it might be neither, right? And so you don't want to waste a bunch of money. I mean, these things are going to be maybe cheaper than manned systems, but some of them are quite expensive, right? So trying to, you want a system that can defend against combinations of threats, but isn't wasting a lot of money, right? Combinations of threats for a period of time that isn't wasting a lot of money. So what we can do is we can say, like, what's the right number of certain types of drones to purchase to maximize your objective against certain threats, right? So you might not know whether you need to buy one of a certain type of drone or 10, again, in combination with all these other types of drones, right? Air surface, subsurface, again, totally domain agnostic. And so what we can do is we can say, okay, you don't know, but here's what the various combinations of all these uncertain inputs to the model will get you. And so what we do is we generate a bunch of portfolios. Again, this is very standard stuff, right? We generate a whole bunch of portfolios. We look at the Pareto efficient frontier, so cost versus the quality of the objective that we achieved. And the point here is it's not, you may not want to buy the portfolio of systems that gets you the best probability of rate annihilation in this case, right? Because what if, the best probability of rate annihilation achieved was 94%, but you could get a portfolio that achieved 93% probability of rate annihilation for half the cost, right? That might be the preferred portfolio. So you don't just want to, maximize probability of rate annihilation without accounting for cost across these portfolios. And again, that's the sort of thing that, clients that are interested in what they should be buying in terms of these systems might want to know.
Yeah. Koa, do you have any questions?
Yeah, Connor touched upon it because I was going to ask, like, so it was far, not, I don't want to say far easier. It was easier to conceptualize and to understand how the other CCA, the distribution network modeling, fits into commercial stuff, like outside of the military and stuff like that. So, but it was interesting to hear you mention merchant ships and everything like that, because I was going to ask, how does Entourage, does it have a applicability towards the commercial market as well? And I guess then, merchant ships and stuff like that probably fall in that category. But would this also be something like, how would they deploy it? Would they do it in conjunction with the Navy, or would they set up their own kind of like scaled back system that used a much more over the counter, for lack of a better word, drones and stuff like that? I mean, it would still be like, I guess, industrial drones?
Yeah, I mean, so I think we as CANA are agnostic. As if somebody wants to build a defensive barrier of drones, I think we can potentially help them out. And so, I mean, what are the commercial applications? I mean, anything where you're detecting and intercepting is pretty straightforward, but that's more on the military side, right? So, I mean, we talked about commercial ships. You can also imagine this being used on land. So if you had a convoy that's moving down through a road network and you want to put out a defensive barrier, that's an obvious one. But I mean, to talk about non-military applications, so critical infrastructure defense, I mean, that's non-moving, so that's pretty straightforward. One can imagine this being used for something like firefighting. So if you want to detect and then intercept fires, something like that. The one that jumped out at me that I thought was kind of interesting. I don't know that I figured I'd get a question like this, like what are other applications of this as a CANA Core algorithm? But I remember reading a couple years ago there was an article about prisons in France, and the prisoners were using drones to fly over the prison walls and deliver contraband into the prison. And what the French did, what the French prison authorities did, was they were using falcons to intercept the drones.
I love
that would be a good idea of something that
I love it.
I don't know what refueling would look like in that case. I mean, I guess you're feeding the falcon. I don't, but it doesn't matter.
Some rodents in a basket over here. Yeah,
we're parameterizing, whatever it is. So if they wanted to use some combination of drones and falcons, Entourage could handle that. And so we actually had coming up with the name Entourage. We had a pretty funny text conversation. But I think what sealed Entourage for me anyway was we were looking at all these different potential names for this particular model, and I think I looked up the definition of Entourage, and I looked up the definition for it, and I wrote it down in preparation for this, but it's Entourage, a group of attending, a group attending or surrounding an important person. And I thought,
that works.
Yeah, that's good, right? You are attending or surrounding an important, let's not say person, but we'll say thing, and that's that's how the name Entourage came about.
It's a good name. I'm hoping that a better name, a nice, ubiquitous, fun name that encompasses it is thought up for the distribution network model in the future.
Yeah, that's a classic name. That was actually DNM was the name given to that particular model before we had written a single line of code, and it is. I'm
just hoping, like I said, that we come up with something that's a nice, sexy name like Entourage for it. They can still have that can be the subtitle.
I'm a big fan of non-acronym names.
Yeah,
not everybody shares my disdain for acronym names, but I like the classic names.
I like the one word. Entourage just comes out easy.
Like I said, I would love a nice, sexy one-word name for the distribution network model there.
I love it too.
I'll take whatever I can. What's that?
So DNM has been a CANA model for years. That was like,
yeah, I know it's been around forever.
The first model I worked on at CANA like 4 years ago, and even within the company, we're like DNM, distributed net something.
Yeah, everybody, the D changes all the time. It's like, wait, is it distributed or distribution or?
Well, I tell you what, I don't think anybody, if we present Entourage to somebody, I think Entourage is a memorable name, and that's
it's a good name. I was happy to see it get picked in the chatter thread there.
Yeah, it hurts my heart, but marketing often beats good marketing often beats good technology in terms. So I think we need both.
Fortunately, we have a good both here, right? A good name and good tech. It was interesting to hear talk about how there might be more. I don't know if robust wasn't the word, but like accurate or not accurate, but like things that could get down into the weeds as far as the algorithms or analytics that go on within Entourage, but it wouldn't be fast enough. It wouldn't be, because you need that computing power to do a good assessment and do everything quickly. But then you still have that, there's that little bit of I'll call it red tape, because it needs we don't want Skynet making the decision. Right? So
depends on how fast Skynet is, Koa.
I guess so, but it needs to get that response really quick. So,
well, no, in this case, I think we were being responsive to the client's needs. So the client had said,
right,
like, they want to potentially use this to evaluate what portfolios of systems that they should buy. Well, that means that you're going to have to run this a whole bunch of times. And actually, I think it's worth mentioning. This is so I've been working with. I have, so there's a nonprofit that I work with called probabilitymanagement.org. Probabilitymanagement.org is about communicating uncertainty, and it's essentially about efficiently communicating the results of models between modelers and people who would use the outputs of models, right? That's a really fancy way to say that modelers, well, let's talk about one type of model in particular. Models involving uncertainty, right? So we think of something like a Monte Carlo simulation. Simplest Monte Carlo simulation you can think of is like rolling two dice, right?
Yep.
You roll dice, you don't know what number you're going to get. That's the simulation. And so Entourage is, at its core, is a Monte Carlo simulation. So what we do is we throw down all these stations of unmanned systems randomly. We run a Monte Carlo simulation of attackers through the barrier that we have defined, because you don't know where the attacker's coming from, right? That's kind of a core assumption of what we're doing. And then you say, what probability of rate annihilation do we achieve? And it might be 0, because perhaps you can detect and intercept it, but you can't communicate that back to the high value unit, for example, right? Or you don't have enough energy to stay on station for the entire time period that you want to cover. So my point is, when you're talking about those 4 things, detection, intercept, communications, and energy, it gets real complicated real fast. And so what we do, so that's the simulation part of it, but then really it's an optimization. So it's a simulation within an optimization. And the optimization is figuring out where to place all the stations so that you can do all those things that you need to do to defend the high value unit. And so my point is, when I was back at Naval Postgraduate School, I taught the spreadsheet modeling course, and I had this great example. We would do what's called the newsboy problem. So it's a classic problem where think of like, it's newsboy problem, cookie sales problem.
Right.
But the idea behind this is that you have to determine how many newspapers to buy up front, and there's a cost to all the newspapers, and then the demand for the newspapers that you're going to deliver is going to be uncertain, and then you're going to eat the cost on the back end of any newspapers that nobody buys, right? Well, this is fundamentally a similar problem to that. And so, but what I would do is I would solve all that in Excel using, I would use the probabilitymanagement.org Excel add-in. So that allowed me to do Monte Carlo simulation in the same way you would use something like Risk Solver or Crystal Ball, except it's free, right? But the really cool thing is I'd run the built-in, so Excel has a couple different optimization tools. It has 3 of them to be specific, and one of them is an evolutionary solver. And I was like, well, I'm running this simulation. Would it be possible to run the evolutionary solver over the top of it to determine what the right number of newspapers is to buy, given things like the cost of the newspapers and the expected demand and all this stuff, right? The shape of the uncertainty or the distribution. And it turned out it was, which was incredibly cool. I used to say, so I would do the whole course, and I used to say, okay, this is like my best trick, right? I'm gonna demonstrate this. This is the best trick I have, and that's basically what I used when I built the very initial sort of proof of concept for the Entourage model. That's the exact approach I used. I did it all in Excel using an open source add-in for probabilitymanagement.org. And using the built-in evolutionary solver. And look, don't get me wrong. That's not what this is. This is implemented in code and everything. And the problem with even the built-in solver in Excel is you can only solve tiny problems, right? They really limit it. You have to go out and buy commercial products if you're going to do serious optimization work in Excel.
And involve it past its initial stage, yeah.
Yeah, but as far as doing a proof of concept and showing that the idea would work, I was able to do that within a week. doing this approach. So that was pretty cool to take what, was, and it genuinely was. Like when I ran that the first time, I was like, there is no way that I'm going to be able to run an optimization using the built-in Excel solver over the top of a simulation in Excel. That's crazy, and it worked fine.
That's awesome.
It was always my
That's awesome. So before we wrap things up, Kassie, do you have any other questions about Entourage and our CANA Core algorithms or anything?
No, I did just want to mention something about our like powered by our CANA Analytics, and I think Connor, just you explaining everything goes to show the people behind the doors at CANA and everything. They really make up, the success of this company and the culture and everything. And so it's another thing that attributes to that. So it's just really cool to hear, I don't know, just your story of, obviously before CANA and how it's played into now. And it really just shows the people behind the doors of CANA really make the motor keep going.
Oh no, CANA has some very talented people that I very much enjoy working with, and along those lines, in terms of like powered by CANA Analytics, like this was a really fun project to work on. So there were a couple projects that got offered up to me, and as soon as I heard like multi-domain drones defending against attacks, and by the way, I'll mention, so this was all before the Red Sea stuff, right? And so I don't know if it was a month or two in, and the Red Sea started heating up in terms of attacks on merchant shipping and everything, and I was like, wow, this might be a lot more relevant than I realized in terms of
good timely solution,
timely, all that stuff. So it was a really fun problem to work on, even when the greedy heuristic for refueling got a little challenging. It took a little longer than I thought it would, but it was a blast to work on.
That's awesome. Connor, it is a pleasure every time we get a chance to talk to you because you have great stories, and it's always a good time hearing stuff.
Yeah.
I am going to wrangle.
I'm glad. I'm going
to wrangle you into a lot of these things would make really great short blogs and stuff like that. And somehow I've got to convince you to write little short blogs for the social media team at some point in time.
That's what AI is for, right?
I don't. We could do that. I want it to have a little bit of that CANA Analytics, CCA, core algorithms flavor to it and everything like that. But we'll talk about that at a different time.
No, all good.
If somebody wants to learn some more about the CANA Core algorithms or get in contact with you, what should they do?
Wow, that's a good question. So, I mean, probably the easiest way is to go on the CANA website and look me up under CANA personnel, and I'm 99% sure my email contact is on there where I would be easy to reach. So that's probably
if not, it will soon be.
Okay, there we go.
Cass.
It's on there.
Kassie, thanks for running everything today and the questions. For everybody else out there, again, like Connor said, you can head on over to CANALLC.com. You can find additional podcasts there. You can find some blogs. Not many written by Connor yet. There's probably, I'll get him to write some and everything. There'll be some other ones out there about the CANA Core algorithms coming from in the past and in the future. And while you're there, you can sign up for our newsletter. You can also hit this podcast up on a couple of the main podcast streaming services. So this is Cobeam signing off for Kassie McRostie, Connor McLemore, and the rest of the CANA Connection podcast crew, reminding you to analyze, assess, and execute. And we'll catch you next time.